we are discussing that how to handle the counting problems with permutation and combination, and mainly the very simple way we have defined the permutation combination problems as the arrangement of ordered and unordered sets, or ordered and unordered selection or arrangement from a set. Now, this lecture will be discussing or will one topic, it is called the derangement. I can simply tell that this is a different type of arrangement or the reverse type of arrangement. So, normally arrangement some property is to be satisfied, we have defined. Now, here also that property is that arrangement should not be there. So, sometimes we tell that this is actually the inverse of the arrangement, and there also this is one counting techniques, because we will see there are many real life problems that comes under this type of topic. So, this is normally called that derangement. So, this is a important combinatorial problems. Okay. So, with one simple example first I try to explain that what is derangement. So, let in a party that 20 people joins, and that 20 people reach there with a hat, that means all people will have a hat. Now, when they leave, then they will collect the hat, and if I give this type of condition that no one will get his or her own hat, and this is one, then how many ways it is possible that no one of that 20 people will get their own hat. So, normally an ordered arrangement will be, we can tell that each people will get their hat. Now, I am telling, why I am telling it is reverse, that means this is some problem that we will be handling, that how many ways we have to tell that how many ways it is possible that no one will get their own hat. So, this is the problem of derangement. Now, first we define that the problem of derangement. So, we are the actual nature of the object is that we can take a set of n elements, okay, like we have considered that 20 person or 20 people join the party with hat. So, I define that thing, that let a set X with n elements as 1 to n. Okay. Now, we define a derangement like that, a derangement is defined that in is that it is defined that the arrangement in which no element gets its original place. That means, I can tell that it is a permutation it is a permutation of say okay, right, I give some variables, permutation of I1 I2 in In of the now elements 1 to 3 up to n, such that I1 not equal to 1, I2 not equal to 2, I3 not equal to 3 and so on. That means, this is the permutation that no one gets this place, means the as if we are taking the place is 1 to 3, that is my right number or place, and then if it is a permutation of I1, I2, I3, In, then I1 not equal to 1, I2 not equal to 1, I3, In not equal to n, that should be that means no one, that is no one in its element in its natural position, no one in its natural place or natural position. So, I define derangement as if the reverse of that thing. So, I can define it is a permutation of this, where if I consider this is the natural position, then no one will get the position, this is my condition to be there. Now, we normally denote derangement of n elements, we denote derangement of, since it is a permutation of n elements, as dn. This is the convention. Now, we see that how we can make the derangement. Okay. Now, what will be d1? Okay. So, we can compute, compute some values of dn, compute dn. Okay. So, what will be d1? If d1, that means I have only one element and say that is position is 1. So, I give I have only 1. Then no derangement is possible, because it is only one position and it is fixed. So, my d1 equal to 0, because no derangement is possible, no derangement is possible. Now, if I have, okay, so d1 is 0. Now, I have d2. Now, see, I get, I have 1 and 2, then that output should be, or the permutation, output of that permutation will be, so I get 2 should be here and 1 should be here. So, this is the permutation I want. That means, only one permutation is possible with 2 elements, that it will be they do not get their position. That means, here 1 in 2 comes here, 1 comes here. So, my d2 is only 1, because I have only one permutation possible. Then what is d3? So, this time I have 3 elements. Okay. I have 3 elements 1 to 3. So, if I have 1 to 3, we see that how many are possible. So, if I have 1 to 3, then one permutation is there, that in place of either 2 can come, or if I take, if it is 1 to 3, in place 3 can come. Now, if 2, then 1 can come here or here, but 1 I cannot put here, then 3 will be in its position, that is not the definition. So, I must put 3 here. so that everyone gets a different place. So, this is a derangement. And for 3, then again similarly 2 I cannot put here, I have to put 1, then 2 will be here. So, that means these are the 2 permutation, this is the 1 and 1, this permutation where that no one gets his proper position. 1 instead of 1 it is 2, 2 gets 3, 3 is 1, 1 3, 1 2. So, these are 2. So, I have D3 equal to 2. I take D4, then I have 4 numbers or 4 elements. Now, if it is 4, this is my original position or the place, then what I can write, that there can be 3 in place of 1, it can be 2. Okay. I can write in place of 1 it can be 3, or this is original. So, in place of 1 it can be 4. Now, if it is 2, then what will be the other? If it is 2, then with 1 3 1 3 4 I have to keep. So, 1 can come here, then 4 must come here and 3. Now, again if it is 2, then see 3 can come here, then 4 must come here, 1. So, 2 1 4 3, 2 3 4 4 1 and 4 can come here, but 3 must be there. So, 1. So, I get these 3. Similarly, I see that if 3 is here, so then it can be 1 4 3, sorry 1 4 2, this can be 1 4 2, 3, this can be 4 4 1 2, this can be 4 2 1. So, 3 1 4 2, 3 4 1 2, 3 4 2 1. So, I get another 3 starting with 3. Similarly, I will get 4. So, this can, if it is 4, then this can be 1, this must be 2, it is 3. If it is 4, instead of 1 here it can come 2, sorry 3, because it is position of 2. So, it must be 3, this can be 1 and 2 and this 4, then it can be 3 2 1. So, 4 1 2 3, 4 3 1 2, 4 3 2 1. So, I get 9, here 3, here 3, here 3. So, my D4 is 9. So, I get that this is actual how we can get the derangements. That means, what are the number of permutations we can get, so that no element can get its own position. So, this is the derangement. But obviously, that if when my number of elements will be more, then it is very difficult to get in this way to count. So, how we can do that thing? So, now if we put the some formula or that some generalized rule whether we can frame. I give a theorem of derangement. So, this is my theorem of derangement I can write. So, I give that for n equal to 1, the derangement formula is dn equal to n factorial 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial plus 1 by 4 factorial minus, in this way if I go, since I do not know what is the value of n, so whether it is odd or even, so minus 1 to the power n 1 by n factorial. So, this is my formula for derangement. Now, how to prove this thing? How we can prove this derangement theorem? If we see that this is nothing but the selection, that as if we have the, see the examples, what this is, when we have 4 elements, as if we have some 4 original positions, and what we are doing, that we are placing the elements in such a way so that no one gets its original position, as if we are considering this is the original position, this is their original position. Okay. Similarly, here it is the original position, this is my original position. So, in the similar way, if I write that, so let S be the set of all n factorial permutations, since there will be n factorial permutations of n numbers if we quickly see with this thing by how it is n factorial permutations. See, I have 3 numbers 1 to 3, then what are the different ways I can permute? Because when I consider that 1 can go here 3 different ways, because one can get this position, one can get this position, or one can get this position. So, when I am considering the first one, it can be 3 positions, but once one is placed for 2, it is only 2 positions. Similarly, once 1 and 2 are placed, 3 has only 1 place left. So, this will be 1. So, this is 3 into 2 into 1, since I have 3 elements. So, this is 3 factorial. Similarly, if I have n, so for n, the first one will get the all n places. For the second one, since already 1 has got the place, so it will be n minus 1, then for n minus 2, and then up to 3 to 1. So, this will be my n factorial. So, that we have written that n factorial permutations of 1 to 3 n. Now, say for some j, say for some j equal to 1 to n, I write some property, some pj be the property like the one we have considered in our inclusion exclusion principle, the property that in a permutation j is in its natural position. J is in its natural position. See, our derangement is that no one will get its natural position, but we note that the property Pj I have taken for all j equal to 1 to n, that means p1, p2, p3, that when I am considering j, that it is a permutation where j in its natural position, j will be in its natural position. Okay. So, that derangement is, if we remember the definition of derangement. So, derangement, that when that Pj gets that means it should be my Pj gets, Pj is the property that j gets its position, and if Aj is that number of if I write that if Aj has the property of Pj, as the property Pj, then actually Aj bar has the property, has not the property Pj, that means it will not get the original position. So, Aj bar has the property with not Pj, that means Pj means it gets its original position, that means it will not get j will not get its original position. So, how actually it is coming with normally the way we handle in inclusion exclusion principle, that we are telling. So, now how that means Dn, I can write the Dn, that this is nothing but the arrangement of A1 complement, A2 complement, A3 complement. That means, if I apply the above statement for all n elements, then no one will get its original position. What I wrote, that Aj bar has the property with not Pj, that means it will not get its original position. Now, if I take for all j equal to 1 to n, then the derangement is that no element gets its original position. That means, 1 will not get its position is A1 bar, 2 will not get its position is A2 bar, 3 will not get its position is A3 bar, and similarly for n. So, Dn equal to this A1 bar intersection A2 bar is n bar, is that, which is nothing but our inclusion exclusion principle. This is my inclusion exclusion principle that we can apply, okay, that we can apply. Then how we will be doing that thing? Now, if I consider my first element, then first element, that what are the way it will take, since, or if I consider the kth element, say, so any ai, first I consider any one element, say Aj. So, I can write Aj can get n minus 1 factorial ways. Why? Because see, I have elements like 1, 2, 3, 4, some GSA, and then n. Now, when it will be getting the place Okay, I will give in a different way. So, I am writing 1, 2, 3, 4. So, I am considering some j n. Then what are the places j can take? J cannot take this place because this is its original position. That means, other than this place, j can take any one of the place. So, j can come here 1, j can come here 2, come here, and some j can go here. So, that means it has option n minus 1. So, what will be the permutation? That means aj can go n minus 1 factorial ways that it can get. So, I can write that it can be the number of permutation that for aj, that it is n minus 1 factorial. Now, for this is for j equal to, say j equal to 1 to any n, that means which one I will be considering first. This will be my n factorial. Now, what will be my permutation then? If I take the 2 permutation, that means ai intersection aj, because if we remember my inclusion exclusion principle, we have to take the 2 combinations also. Then if it is 2, then simply it will be the similar logic. I can give it is n minus 2 factorial, because now already 2 elements have placed. So, I have to or 2 elements, they will not get their original position. So, I have to discard those 2 places. So, this becomes n minus 2. In this way I can write this thing that a1, I can write that a1 intersection a2 intersection a3 intersection ak, that will be my n minus k factorial. This will be my n minus k factorial. So, now if we try to utilize my inclusion exclusion principle, so it will be of, there are, since another thing I require, that since there are nck ways I can choose, nck the k combinations of 1 to n elements, that numbers that I want to put. So, now if we apply inclusion exclusion, principle, inclusion exclusion principle, then how we get, because already we have seen that dn I can define nothing but my a1 complement intersection a2 complement, like n or this complement of this thing. So, if I get that all permutation, earlier what we have seen, that means no restriction, this will be n permutations, minus this is my NC1. I see that there are, this can be there, and for 1 there can be n minus 1 factorial permutation, and that 1 I can choose from n. These NC1 ways I can choose the first element, and for each n minus 1 factorial. Now, I can for 2 elements I can choose from NC2, and for 2 we have seen the number of permutation would be n minus 2 factorial. This will be the next will be the similarly NC3, then n minus 3 factorial, and if I go in that way, then for nth minus 1 to the power n, then NCn n minus n factorial, NCn this is n minus n factorial. So, now if I put this thing, or if I compute n factorial minus NC1 n minus 1. So, this n factorial divided by 1 factorial into n minus 1 factorial into n minus 1 factorial, plus second term is that n factorial by 2 factorial into n minus 2 factorial into n minus 2 factorial minus, if I go in this way, this will be minus 1 to the power n NCn. So, I can write n factorial divided by this n factorial into 0 factorial, and n minus n is 0 factorial, like that. So, see that here actually that each term from the denominator and the numerator, that one term is always same. So, these are equal, and so this will vanish. So, if I continue, then I have the dn equal to, I can write n factorial, I can write dn equal to n factorial minus n factorial by 1 factorial plus n factorial by 2 factorial minus n factorial by 3 factorial. In this way, if I go, then minus 1 to the power n, then n factorial by n factorial. This the last term, if we see that 0 factorial, it will cancel, and then I get, if I take n factorial common, then I will be getting 1 minus 1 by 1 factorial, 1 by 2 factorial minus 1 by 3 factorial plus minus 1 to the power n 1 by n factorial. So, this is the theorem statement that we get, that we can prove that this is my derangement expression. Now, I can put some compute, because earlier we have seen that only say some simple values or some small values of n we can easily compute. So, now we can put up to 4 we have done. So, if it is d5, now I give the expression 5 factorial 1 minus 1 by 1 factorial 1 by 2 factorial minus 1 by 3 factorial plus 1 by 4 factorial minus 1 by 5 factorial. So, it will be, it comes that 5 factorial minus 5 factorial by 1 factorial, 5 factorial by 2 factorial minus, so each one term will be plus, one will be minus 5 factorial by 3 factorial plus 5 factorial by 4 factorial minus 5 factorial by 5 factorial. So, if I compute, we will be getting that, okay, quickly I do that, this is again 5 factorial, both will cancel, then it is 5 factorial by 2 factorial, means this is 5 into 4 into 3 minus this is 5 into 4 plus this is 5 minus 1. So, these will cancel and it will be 60 minus 20 plus 4. So, this becomes 44. So, my D5 is, so I get another value D5 is 44. I get my D5 is 44. Now, see, we can compute since I got expression, but fortunately there is another very nice expression we can get, and that is some recursive statement that we can recursive expression that we can get, recursive equation for Dn. So, I can write actually we can prove easily if we can use that expression for Dn, then I can write Dn is n minus 1 into Dn minus 2 plus Dn minus 1, and this is for n equal to 3, 4, 5 I can write. So, now easily we can, if we can put, we can get D3 equal to 2 into D1 plus D2, and already we got D1 D2 is 0 plus 1. So, this becomes 2, then D4 equal to 2 into D1 plus D2 plus D3. So, this becomes 2 into 1 plus 2, this becomes 9. Similarly, I can 2 into D3 plus D4 is equal to 2 plus 9. Okay, sorry, D4 becomes 3, it is n minus 1 is 3, here n minus 1 is 4. So, this becomes 44. Similarly, I can now compute more values, that n minus 1, this is n minus 4, this is 5, D4 plus D5 is 5 into 9 plus 44, this becomes 265, and in this way I can compute, and we can easily compute all the derangements of these things. So, once we get the derangement, now easily we can apply this expression, and particularly this recursive expression will be very easy to get the derangements, and the problem that we started, that example, that easily we can use that thing. So, one quickly if we see one example, that what earlier we are giving, that some in a party, that if n men and n women, they wish to join turns and how many ways that they can choose so that the n women can get a male partner, first time. So, that is my n factorial. So, if it is first time, we remember since I have 1, 2, 3 simply n, I have also 1, 2, 3 n, I have these women, n women, n men. So, simply there is no restriction, n factorial ways the first time they can get. Now, if second time we want, the restriction is that everyone has to change the partner. This is my restriction. That means that derangement. Everyone has to change the partner. Then this is that actually the nothing but the dn. So, this is actually the second time turns. So, if it is second time and this is my restriction, so this is dn. So, simply that using dn we can solve this type of problem of combinatorics. So, with this lecture we finish the lectures with the combinatorics problem, that how to handle the counting techniques with combinatorics problems.